Fine.
Sure. Okay. Let us start the section, sir.
Yeah.
We welcome you all for the second section. I'm extremely honored and privileged to welcome Dr. I.V. Muthuvijayan Ninoth, sir, Technology Head, Center for Nanoscience and Genomics, Karanya Institute of Technology and Sciences, Coimbatore. With 15 years of teaching and 21 years of research experience, Sir published more than 100 articles in reputed high-impact scientific journals, mostly as either first or corresponding author. And Sir have a major project funded by Department of Science and Technology, Government of India has been successfully completed. And at present, a major project funded by Department of Atomic Energy, Board of Research in Nuclear Sciences is under progress with Sir as Principal Investigator. Sir have doctoral students, MPhil and PhD students already completed and working. Sir's research interests are in magnetic and luminescent nanomaterial for cancer drug targeting, supramolecular host gas chemistry and drug DNA interactions. With this simple introduction, I am happily inviting Dr. I.V. Muthuvijayan Ninoth, sir, for technical section 2 entitled on Smart Materials in Chemotherapy. The section is over to you, sir.
Thank you very much.
Thank you, sir.
Yeah. Is it okay, ma'am? Is it visible?
Yes, sir, it's visible.
Right. So today we are going to discuss smart materials in therapeutics. You know what is meant by a smart material? The term smart was added later by the end of the 20th century. And you see here, much before the concept of smart materials developed, there were reports on such materials, and one material that occupies among the plethora of smart materials is hydrogels. Hydrogels basically are polymers that can absorb water, and they can swell, they can respond. So this immediately explains what a smart material is. It should respond to stimuli, it should change shape, or it should provide a signal. That is the idea behind a smart material. It could respond either to light or heat or pH or electricity or magnetic field. These are some of the stimuli. These are the physical stuff we have available in our arm tool, which we can use to manipulate these objects to make them respond to the stimulus. The first studies related to hydrogels appeared in 1894, more than 100 years ago. But that was not considered, in a way it is considered now for applications. Look at this. This is the actual image of hydrogel that looks like it is a glassy substance. Of course, it has the aqua which is loaded inside. This material has swollen. As such, the material looks like a powder, and when it absorbs water, it looks like a gel. That's why we call it as a hydrogel, obviously. Much of the work has been done on imparting other properties to hydrogels, making them magnetic, making them luminescent, and making them responding to pH and other stimuli. Basically, it absorbs water, moisture, and the functional groups in the polymer should be designed in such a way that they have a good interaction with water, and the water holding capacity also can be quantified. And that finds an application if it is biocompatible. A lot of applications are there in tissue engineering, implants, and other biomedical applications. This is straight away explaining how it is applied. Some stem cells are isolated. This is one example where the hydrogel is applied. The stem cells are cultured. They are allowed to proliferate, multiply, and then you add the hydrogel. The hydrogels have strands that are cross-linked, and they have walled spaces between them where the cells get into, and these grow as something like a tissue, and that is injected in the bone marrow, and you find that working something similar to a bone marrow. This is the best example that describes a smart hydrogel. And in the middle of the 20th century, they were termed as water-swollen cross-linked polymeric networks. They are, even though considered just as a polymeric network, the term was coined later, as I said. You look at the structural features of such materials. They have a central strand. Some molecules are semi-bound. Some molecules are still there, adsorbed on the surface, something like a free water molecular layer, and that is something like a gel finally. So the physicochemical aspects of such structure should be understood that way. How far they are swollen, how the volume increases, what kind of hydrophobic or hydrophilic interactions they have, how much of the hydrophobicity is contributed to that and hydrophilicity is contributed. That depends on how far they can hold the organic molecules inside them. And you find out interstitial water molecules that stand between two strands of the polymers. You can't just say them as polymers. You can view them as just polymers, but they have this unique property. That's why they are called hydrogels. There are several polymers. What comes to our mind when we say polymers is with our own perspective. So hydrogels should be clearly defined, and you make them smarter by introducing light responsive groups or introducing some magnetic nanoparticles into them to make them magnetic, or anything which responds to the change in pH. Groups that may get protonated or deprotonated will make them responding to uh, the pH. Can you give me some 10 seconds? I'm sorry about it. Thank you. So these are hydrogels that find applications, and when they are integrating with the tissues, they fully dissolve. They act like scaffolds that build the natural growth of the tissues, natural cell growth around them. They act like some kind of templates for the cells to assemble and then digest them, and they are integrating into the tissues first, and they actually disappear. They are very interesting materials. So that's why I have put them in the first list, in the first position of the list I have chosen. In fact, I will talk about three classes of materials. Of course, one kind of materials can be called as molecular materials. The other one is something on the materials that respond to near infrared radiation, and first I will discuss hydrogels, and these are, without these you cannot imagine smart materials of today. See, the word smart was introduced in 1948, I said by the middle of the 20th century, by Kuhn and co-workers. They are smart because they can detect the prevailing stimuli, as I already said. They respond to the structural, morphological, or functional changes. And they have unique properties that can be associated with the environmental factors. That's how it was first defined, and much of the work started with this perspective, and most of them were pertaining to the application in the drug delivery and in biomedical field. So drug delivery, tissue engineering, and so on, they are made more and more smart. They become smarter and smarter. The first publication about the polyacrylic acid. Polyacrylic acid is one polymer that can respond to stimuli. The first publication was about the polyacrylic acid molecule that could undergo structural adjustments according to the pH of the medium. And here is the kind of chemistry that is well known now as the supramolecular chemistry, because it deals mostly with the non-covalent bondings, building larger structures starting from the smaller structural units. And that is applicable to the development of smart hydrogels. You use the principle of supramolecular chemistry actually to construct larger structures. Finally, the morphology emerges out for the hydrogel with a series of variables, and that is finally starting from the structural design. You are using that with a particular design in mind, and the structure, the chemical synthesis is chosen with the structure, final structure in mind, and the supramolecular chemistry principles. See, the monomer composition and the ratio of their composition also should be tuned. Let us say it is a copolymer. One part may be a hydrophobic part, the second part may be hydrophilic part. The extent of polymerization can be decided. What is needed should be taken into account, and then it should be decided whether you want hydrophilic polymer, more hydrophilicity or more hydrophobicity. That should be designed. And what is the stimuli? The stimuli are called inputs. You consider that as input. Just compare that with a machine, compare that with a computer. You are giving inputs, maybe an electric pulse as an input. And what is read are the magnetic parts. The magnetic parts are read by a laser maybe. So these are all how the memory is stored and retrieved. Something like that. You call these molecular stimuli or the light or magnetic stimuli as inputs. And what is the response by the hydrogel is called the output. Okay, so you have to design that on a rational basis, and you are imparting some property to the polymer. You do not prepare something and explore it for its properties. That's the reason you call that as a designed hydrogel. That's why you call that as being smart, and you are imparting smartness to the hydrogel. And a set of criteria has been used to classify these systems, including the origin, the degradability, and cross-linking mechanism. Polymers may be linear strands. They fold, they coil, and when they coil, they can coil and recoil. The interaction between the folded strands may be weaker or stronger. So you can make them stronger by inducing a kind of chemical bonding, non-covalent bonding between them. If you have some part of the strand having negative charges and the remaining part having positive charges, they will fold and form a stronger interaction. They will be in mostly folded form. The folded form is interesting because even though they are folded, they are not covalently bonded. It's just a weak interaction, and water can get into that. Just look at the left bottom corner. It is something like a fiber mat. It is three-dimensional mat. You should say, and into the three-dimensional void spaces, the water molecule can get into and swell them. So before the swelling and after the swelling, the volume is dramatically different. So that is why you are imparting, that is how you impart the properties to these structures. You are manipulating the factors involved in these links. And finally, you construct the system in the macroscopic form. And some responses are expected that can be manifold, and it can include degradation, drug release, swelling, changes in shape or surface. These are the properties that are pertaining to these smart hydrogels. A conformational modification, everything we studied in basic chemistry are put together in its modern form. Hydrogen bond is a good old scientific concept explained by chemistry for for decades, of course, but even after the understanding of the hydrogen bonding, there was one question: where does the energy of hydrogen bond come from? Of course, it's when a hydrogen stands between two electronegative atoms, it is understood having a hydrogen bond with one of the atoms, one of the electronegative atoms. That is a common understood hydrogen bond. But what drives it? What is the driving force behind that? What is the thermodynamics involved and the free energy contribution by the formation of the hydrogen bond? These were all questions for a longer period of time, and one of the textbooks, popular textbooks, states that to the question where does the energy of hydrogen bond comes from, there is still no concise answer that seems to be generally acceptable, and there probably never will be. That's the statement given in one of the popular inorganic chemistry textbooks. That's that was the energy dedicated in understanding the hydrogen bonding. And hydrogen bonding, of course, was converted into the concept of supramolecular chemistry. No one talks much about just the bonding, but about the final structure. Even though the fundamental chemical driving forces we discussed today are well known to us in its elementary form as we studied in your graduate and undergraduate program, what comes to the research field is finally the application, and that is how you articulate the results you do in the experimental work in the research laboratory, and that is to be articulated in terms of the applications. And the smartness you impart here comes from the stimulus and how the response is. And it's not just the pH. I said I will explain what are the stimuli and how it responds, citing out some specific examples. What is the application of that? If it is having a void space, is it can hold molecules that can be released at the expense of some stimulus. There is one popular statement that anything that is having a void is interesting. Anything that is having a hole or some space, some cavity is more interesting than a rigid structure that doesn't have any void. In other words, anything that is having a flaw is more important than anything that is perfect. Any perfect structure is not important. Anything that is having some mar or void, some space is more interesting. That is the description by material scientists nowadays, especially those who work on nanotechnology. And you find out such nano-sized pores important. You can say sometimes you observe that hydrogels being termed as nanogels, sometimes as microgels. What is the difference? Finally, the structure may be in micro size scale. You call that as a microgel. Sometimes you prepare nanoparticles, polymeric nanoparticles, and they still have these spaces. Now comes a question: if it is a nano size scale, assuming that they have 200 nanometer, anything below 100 is generally understood by the public as being nano sized. Let us say it is 100 nanometer. Assume that it swells 3 times or 4 times and it becomes 400 nanometer. How do you call that? It is close to the micrometer regime. So how do you call that as a, how do you call that, a microgel or a nanogel? This is a question by lay people, but still it may be called as a nanogel because the pore size is in the nanoscale. So the pore size, the cavity size is more important. So that's how we should understand the materials. And finally, a general word should be put that if you are so stubborn on the size scale, you will miss out interesting structures in the micro scale regime. That's why some journals are like micro nano. Journal, the journal small has a suffix called micro nano. So in order not to miss the important structures in the micro scale domain, these should be put together. The nano and micro should be put together as far as the chemistry is concerned. Everything depends on what kind of application you want to derive. So these questions are very common in any PhD defense. People are always concerned about size because that is a question they can easily ask. Why is it not in nano size? It is 120. So strict officers, they ask. So finally, what is the what we derive from that is what's more important. So nanoscale is here important when you talk about the pore size, because these pores can hold the molecules, drug molecules. Many are there, many drug molecules have the angstrom size scale, and when they are bigger molecules, they come close to 2 nanometer or 3 nanometer, and such molecules can be accommodated in hydrogels. Some hydrogels are responding to temperature. I gave this example in my other lecture. There is that polymethyl methacrylate that responds to heat, that is used in magnetic hypothermia. That is a kind of internal heating. And some of the polymers are responding to heat because they change their conformation. Maybe the hydrogen bonds between the conformers may be broken, or they change their conformation by twisting or unfolding. So they respond to temperature. The temperature, you cannot state it randomly. You should mention the lower critical solution temperature and upper critical solution temperature, because otherwise it would be difficult to describe them. And these properties are so essential to know whether they are mixing with the solvent. See, lower critical solution temperature refers to the conversion of two phases into one phase, below which the phase is 1 and above which the phase is 2. What does it mean? The polymer may be a kind of partially soluble and it becomes fully soluble below one temperature. We call that as a lower critical solution temperature. And there comes a temperature where above that there will be one phase. You call that as the upper critical solution temperature. And much of the studies were related to knowing such lower and upper critical solution temperature. This is better definition and better understanding of hydrogels. You understand how the hydrogel concept started just from the polymer chemistry, and how just the increase in the volume, the swollen property was understood, and then insight was extended. That's how you understand the lower and upper critical solution temperature. And from 2005 and 2010, when you want to explain something as a thermoresponsive polymer, you should mention the critical solution temperatures. Even in some other journals also, when you talk about polymers, they ask the critical solution temperature. From 2005 to 10, there were only 44 publications that were dedicated to the upper critical solution temperature, and 330 including the lower critical solution temperature. And now Many papers are discussing this. There is dramatic growth in the better understanding of smart hydrogels. At 20 degrees centigrade, they may have one conformation. They may be folded. For instance, what you see at the right side, and they may even break, or they may change their conformation and release the therapeutic that is loaded in them. The smart gels are thermoresponsive in this particular case. I said at a lower temperature, when you are considering hydrogels that have a clear-cut lower critical solution temperature, water molecules are arranged around the polymer because they form a water of hydration around the polymer. Nothing but the hydrogen bonding on the strands of the polymer. So it is more like a layer of water on the polymer strands, and the temperature increase reduces the energy associated to the water polymer interaction. So some of the water molecules are expelled out. So when the polymer dehydrates, transformation occurs and there is more hydrophobicity. So when water molecules are fully surrounding these polymer strands, the entire structure looks something like a hydrophilic form. And when they are expelled out, when the water molecules are expelled out, there comes the natural organic property of the polymer, which is hydrophobicity. And this is one example. You find out the N-isopropylamide, you call that a polynipam, and that responds to temperature, as I said. And you look at the temperature change and the performance and the transformation of the structure is, see, exactly at 32 degrees centigrade that happens. So the structural change is there at a particular temperature, and that temperature also should be mentioned. So that the temperature is finally the change in the conformation or the change in the structural form that allows the tuning of the hydrophobicity and hydrophilicity. So you are making the structure responding to temperature and changing its structure that helps the release of the drug or loading of the drug. Some other examples are pluronic and tetronic. These are also polymers. They have a large, OH groups, OH group at the end group. Okay, one end is OH group. What is the advantage of having OH and NH2 at the end group? They can be chemically modified. You can attach a fluorescent molecule, for instance. You can attach a drug directly to the end of the polymer by covalent modification. That is also possible, or it can be just the physical mixture where the molecule gets into the strands, into the void spaces. If you look at the pluronic structure, you have OH at the end group. The center has the monomers have one methyl group that imparts hydrophobicity, and O is there, ethyl O is there, that O can absorb water molecules. So the hydrophobicity and hydrophilicity go together in pluronic. And in another case where you find the hyaluronic acid has a COOH function, and the COOH again can be functionally modified, for instance with the DCC coupling, dicyclohexyl carbodiamide coupling. You can attach any amino group to that, making it an amide. So hyaluronic acid can also be functionally modified. There are several options. When we discuss polymers, the advantage is that they can be functionally modified, they can be folded in a way we want them, or we can impart both hydrophilicity and hydrophobicity in a precise manner. More of hydrophilicity, you want more hydrophilic groups to be added. More hydrophobicity, you want more hydrophobic functions should be added. It could be a copolymer having one monomer hydrophobic, the other monomer being hydrophilic. So It can be a polynipam hyaluronic copolymer also. So you add the properties of nipam and hyaluronic acid together in one structure. This is one example where you see the hydrogels are injected into this organism where you find such a swelling. See, these are utilized for drug-loaded, drug-releasing materials being implanted, or it can be used in aesthetic surgeries. Look at this. These polymers are adhering to the cells. At one temperature, they become non-adhesive. What does it mean? You can tune the interaction with cell. Why they should interact with the cells more at one particular temperature? Because they may be swollen, they can, the surface hydrophobicity may be different due to the conformational change. So all these can be tuned. That's what is observed in the SEM image. Look at that. The structural change arises clearly due to the change in temperature at 37 degrees centigrade. The morphology is different, and 20 degrees centigrade, the morphology is again different. So all these are temperature responsive materials. I said the hydrogels are responsive to temperature. Here we have a set of compounds that are responsible, they are responsive to light. They change their conformation with respect to the absorbed light. The photosensitive polymers, you call those as photosensitive because they change their conformation at the absorption of a light photon. One basic molecule that responds to light is azobenzene, you know. The azobenzene is a chromophore that absorbs a specific wavelength, or it could be spiropyrin. I'll explain the spiropyrin in detail in some of the later slides in some other category. These conformations are changed when a light of a particular wavelength is passed. When they change their conformation, obviously the strands they twist, they change their shape overall. The pore size may be increasing. You call them as photosensory polymers, and they can change their physicochemical properties, or they may even degrade. How do they degrade? The light can break some of the bonds. In some cases, when the molecules are making the bond to shift and break, molecular rearrangement can happen, allowing two molecular fragments to be formed from the one large molecule. And if these molecules are part of the polymer, that structural change also will arise. It could be a conformational change, or it should be a structural change. It could be photopolymerization also. Some molecules can get the light absorbed, and they can form free radicals, and then they undergo further polymerization. Free radical polymerization is an important mechanism in the polymerization, and further polymerization will make them more rigid. So a kind of gel may become even a stronger solid. Okay, so these are all possibilities, and you impart property change in response to light. This is one example. You see the diazo molecule being attached to a polymer strand. The diazo molecule may be encapsulated by cyclodextrin, as you see the bucket shaped molecule, the green color molecule at the center, that may be complexing the diazo group, and when the structure changes, that may be released, the cyclodextrin may be released. This is one common idea. With cyclodextrin you can do a lot of play of molecules, and when that is changing, you look at that image B, the diazo molecule in one conformation complexes with cyclodextrin. It is a host guest complex, and when the light is passed, the conformation of the diazo group changes. It is more becoming cis configuration, and when it is becoming a cis isomer, it pulls out from the cyclodextrin, it becomes decomplexed. The host-guest association is disrupted and the strands are separated. So what does it mean? Whatever therapeutic you put inside, you see the green color stuff you put inside is a folded protein molecule. The protein is actually acting as a drug. The protein is inside the cavities, and when you are passing light, the strands are separated and the protein gets released from the hydrogel. So these are all light responsive hydrogels. That's a very interesting report in Chemical Communications journal. This is another case where light responsive hydrogel acts. You see, the association can be disrupted with passing of light. Okay. That again relies on UV light. So what is the disadvantage of using UV light? UV light, of course, is energetic and you can use it for cross-linking of strands, or you can disrupt a strand depending on what kind of reaction the groups can undergo. But the disadvantage is that they undergo low penetration. They have a shorter wavelength. Shorter wavelength means low penetration of the radiation. But low wavelength means high energy. Shorter wavelength always mean high energy. High energy means they can do some damage to the tissues if you have an application in the biomedical field. And they may be potentially carcinogenic also, because UV radiation, when it falls on tissues, they may induce a kind of reaction that causes free radicals, or it may cause some tissue damage that induces the benign tumor, as I explained in one of the other lectures. So how to overcome that? You can avoid using UV radiation and make the polymers responding to near infrared. That comes at a longer wavelength. That's something which is in the visible light or in the near infrared radiation range. If you are using polymers that respond to such ranges, they may be safer. So, okay. So they are light responsive polymers, light responsive hydrogels. Some hydrogels may be responding to electric and magnetic fields also. These are electro-responsive systems. What you see at the left side, left image, you see there is a carbon nanotube on which a molecule is wounded. It is wound. That wound molecule has a functional group that is attaching a strand, a polymeric strand. What does it mean? The polymeric strand makes the structure hydrogel. It makes it a hydrogel, and the carbon nanotube is attached. Carbon nanotube is imparted to make a kind of rigidity to the structure. Carbon nanotubes are strong structures. They are stronger than steel. If you are comparing, see, by the way, if I say carbon nanotube is stronger than iron, that is actually disturbing. That idea is disturbing. Carbon nanotube is soft. Why do you say it is stronger than iron or steel? You consider steel at the nano size scale, a wire of steel at the nano size scale, a carbon nano wire. You compare, pull them. The steel will break at that size scale. That's how we say carbon nanotubes are stronger than steel. The carbon nanotubes can withstand such stress. They have a higher Young's modulus than the steel. So they are stronger. That's the idea behind using these carbon nanotubes. Or they may have some fluorescent property also if they are carbon nanoparticles, carbon nanodots. In this case particularly, we look for the properties of carbon nanotubes being in association with the polymer that may act like a hydrogel. You attach the hydrogel. See, this is they have some end groups that have some diazo group. It's not. It's like azole ring. It has an azole ring, and interestingly, they can form complex with copper. copper 2 plus. So this can be exploited, this property can be exploited to make them responding to electric field. You put them in an electrochemical cell. What does it mean? Copper 2 plus can be converted to copper plus. You can reduce that. Cu2 plus getting reduced to Cu plus. The Cu plus does not interact with these end groups. Cu2 plus interacts. So what does it mean? When they are interacting with the end groups, the structure gets connected. You are doing it in combination with an electrode. These molecules adsorb and they form a kind of gel, hydrogel, and they are associated at one condition. And when the oxidation number of copper changes, when the copper is decomplexed, the strands break. That's the idea behind using the electrochemical principle. Here they are electro-responsive systems. And these hydrogels can respond to magnetic field also if you are incorporating a magnetic nanoparticle inside. I discussed spions in the other lectures. Super paramagnetic iron oxide nanoparticles can be called as MION also, magnetic iron oxide nanoparticles. You can incorporate them in the polymer matrix. One day you come and say you use them as nanoparticle and this polymer as just the coating polymer and you call it as a magnetic nanoparticle. The other day you come say that as a hydrogel and you put that magnetic nanoparticle inside. Why these different terminologies, you may ask? Here the composition is mainly the polymer and you exploit mainly the property of the polymer, and these magnetic nanoparticles are just additives. They are occupying the space of the polymer. And in the other example where I said polymer coated magnetic nanoparticles, the size of the magnetic nanoparticle is larger compared to the layer of the polymer. They are just used to cover the surface of the magnetic nanoparticle. Here the polymer structure is actually the microstructure we are studying, and magnetic nanoparticle can occupy some of the spaces. It depends on the mass proportion also. And they are made magnetic, they respond to magnetic field obviously, so they can be magnetic responsive materials. Okay. So you can pass an electromagnetic radiation also, make them respond to the field, or you can apply a large magnetic field so that they can be oscillated. When you are oscillating, you are physically disturbing them. When you physically disturb them, the molecule inside can cut loose and come out. And you see, they also can be pH responsive. I said electro-responsive, magnetic responsive, and they may respond to other stimuli also. Here is one important stimulus, that is pH. pH is a very interesting stimulus. pH is understood something like a negative log to the base 10 of hydrogen ion concentration, just that definition, that's all. That's how our students understand. pH is so interesting. pH is a very important property in the context of physiology, in the context of a drug delivery. The human body exhibits substantial pH changes in different body parts, although it is understood having the common physiological pH 7.4 to 5. The pH is, on the other hand, as understood, it is not the same in all the places. It is around 1 to 3 in stomach, you know, that is an acidic pH. 1 is a large acidic condition. In duodenum, it is 4.5, 4.8 to 8. It's largely varying from 4.8 to 8.2, even up to the basic condition. And colon pH, of course, is normal. And inside the cells, the cell organelles may hold some kind of pH around them. So exploiting these pH conditions can allow specific drug release on their site. So the hydrogels, if they are responding to a specific pH, for instance, low pH. So how can we exploit the property? They can be allowed to work specifically on stomach. If they have a larger pH, they respond to a larger pH like 8.2, they can be allowed to work only on duodenum. This is interesting in the context of cancer. It's difficult to target one particular organ where the cancer arises. The chemotherapeutic treatment is seeing all the organs unified. It's difficult to find difference. That's why we look for the attachment of ligands that search for specific receptors. Here, this hydrogel can be made to work based on the pH itself. How to do that? The polymer should have specific functional groups that respond to pH. Obviously, carboxylic acid function can get deprotonated and the pH can become larger. It may be at a lower pH. When it is deprotonated, it can become a larger pH material, or it can be having NH2 group that can be protonated, may become NH3 plus. Another advantage of these charges also are there. These charges make them getting repelled between them. So the swelling is facilitated by imparting charges. So you do a kind of dissociation of the groups, and you should be very clear about the pKa value. pKa value is the exact pH in which the dissociation takes place perfectly. It should be 50% of one form, 50% of the other form, and the pH corresponding to that is called the pKa value. You know, that should be known. The pKa changes for several structures, for different structures. For one structure it may be 1 pKa, the other structure the pKa may be different, and that again can be different under the condition of light also. See, you are using electromagnetic radiation, the molecules respond to light. Both pH and light, if they are used as stimuli, the pKa value may be different in the presence of light. The pKa value may be much different from the original case I said. In the presence of light, in the absence of light, the pKa may be different. So you have more stimuli that can be used in tuning the hydrogels and their function. This is one example of a pH responsive hydrogel. There are two examples actually, alginate and chitosan. One is having COOH group, the other one is having NH2 group. They are pH responsive. These are natural. That's why these examples have been chosen. Alginate, chitosan, these are very much biocompatible. Chitosan is present in the shell of organisms. Chitosan is present in our body, pectin, gelatin. These are all common structures. You can have such polysaccharides like alginate having a functional group that can be made to become O minus group, NH3 plus group. So light, temperature, pH, and now comes response to molecule. Glucose can do a stimulus in these structures. What is the advantage of glucose being used as a stimulus? The molecule binds specifically to certain hydrogels and do some trick. See, these are the glucose responsive polymers are used in diabetes treatment. A large amount of glucose will be there in the blood, for instance. So you use a glucose oxidase that is on the strand. Glucose oxidase is on the polymer strand. What will happen? The glucose oxidase has a receptor for the glucose molecules. When it binds to the glucose oxidase enzyme, the glucose molecule is converted into gluconolactone and hydrogen peroxide, that is oxidase actually. That glucose you can actually measure how much of glucose is there. See what will happen in the context of hydrogel. When the glucose goes binds to that, the polymer again is swollen. There is a receptor. See, this is the structure that best explains that. The green color is a receptor for the glucose. The glucose goes binds, and what does it mean? It pushes these strands apart. So that makes the polymer strand swollen, and the cavities are becoming larger. So in case you have a load of insulin or any drug that treats the diabetes, for instance metformin is a molecule that is treating diabetes. So if you are putting these therapeutics inside, when glucose goes binds, the hydrogel is swollen, the drug is released. So they can be used for implants in the case of diabetic patients. So that is one case, one class of compounds I discussed. Let us go to the second class. I think I'm going slow, but I'll try to complete. The second class of smart materials, they respond to the radiation. These are called photothermal therapeutic agents. This treatment that is specific for cancer, this is much needed and considered essential for the treatment of cancer. They respond to the electromagnetic radiation in the NIR field, near infrared field. As I said, NIR is a safe range of wavelength. UV will again cause damage to the tissues. One best example is gold nanoparticle. Of course, this is the first material that was reported for photothermal therapy. The gold has a plasmonic band. It shows an absorption band at a longer wavelength apart from the natural band. The longer wavelength band arises from the so-called surface plasmon resonance. Everyone may be aware of that. And that band can be tuned based on the size of the gold nanoparticle. If the size is smaller, it goes to a shorter wavelength. It may go to a longer wavelength if the size is larger. Also, it depends on the shape of the nanoparticle also. And that has, this gold nanoparticle has plasmons. You should know what is plasmon first. See, the shape is different. I'll come to the definition for plasmonic band and the plasmonic heating. Gold nanoparticles being metallic structures, they have a loosely bound electron on their surface, and that again is varying due to the size. You know, most of the atoms are present on the surface. When it goes to the nano regime, the shape also does some trick. You know, these gold nanoparticles have been prepared in different shapes. Gold is one nanomaterial that has been tried from left to right in all sizes and shapes. These are so interesting. Nowadays, gold nano stars are also made. Gold nano stars have been found more useful than the spherical nanoparticle, spherical gold nanoparticle in the context of photothermal therapy. The surface plasmon resonance refers to the oscillation mainly of the electric field gradient of the electrons on the surface. They are a kind of, plasmons, are called as the, a separate form of matter. Plasma is called a separate kind of matter. The plasmons are similar to that, they are on the surface. Plasma and plasmon are slightly different. A plasma is an ionized atom. The plasmon are loosely bound electron, and they are not. Plasmon does not refer to the physical matter. Instead, the wave associated with that. That is how we have to understand the plasma. That is how I can best describe that. The kind of the oscillation on the surface, that energy associated with that, you call that as a surface plasmon. And the surface plasmon band is common for gold and silver nanoparticles. These metallic nanoparticles have these surface plasmons. and they can be excited using radiation, an NIR radiation. For instance, the near infrared radiation that allows the heating of the structure. That radiation is absorbed and the relaxation allows the heating of the particle, and the absorption of the NIR radiation is measured in terms of the absorption, and the heating of the nanoparticle is measured in terms of the photothermal conversion efficiency. Look at the wavelength. It starts from 400 and 580. It goes up to even 800. This 800 is an interesting wavelength. 808, something close to 800, is the normal laser radiation that is used for excitation of this gold nanoparticle, that is to be used in photothermal therapy. 808 nanometer laser. But nowadays attempts have been made to shift even further the wavelength to the NIR2 range. That means that starts above 1000. Look at the nano shell absorption in figure D, that goes even up to above 1000. So there can be a laser, normally 1064 nanometer laser, that is a diode laser that can be used to heat the radiation, heat the particles and derive the heat. See, look at this, why you have to choose the specific wavelength of excitation. Normally the molecules in water, the tissues, they have some absorption, some strong absorption is there below 600 and above 900 up to 1000, and the range between 680 to 900 you call that as an NIR window, because that is the range where the absorption is low. What will happen? The absorption will only be due to the nanomaterial incorporated, and it will not be absorbed by the tissues. The red color refers to the oxidized hemoglobin, green color refers to the hemoglobin absorption. Water absorbs, you see the blue color spectrum, and water, the oxidized hemoglobin and hemoglobin, all these absorb low in this range. You call that as NIR1 window. So you can choose a wavelength that is suitable for heating only the nanoparticle. Selectively it will heat the nanoparticle. That best wavelength is 808. 690, 750, all these wavelengths also were tried earlier. Now it is understood that longer the wavelength, better it is. So 808 is commonly employed for photothermal heating, and there is another window above 1000. You call that as NIR2 window. That NIR2 window, of course, is very interesting, and the absorption by the tissues, the natural tissues, is low. Absorption by the material is larger, and that will not cause harmful effect to the tissues also, because the wavelength is longer and the energy is short, the energy is lower. But the problem is you have to design NIR2 materials. These gold nanoparticles absorb commonly in the NIR1 window. Maybe some gold nanomaterials may be made to absorb in the range 1000 and above, but it's difficult. The preparation procedure is difficult. The size is also not in this suitable range. So we look for newer materials. The way in which the gold heats up is plasmonic resonance, plasmonic heating. And the other materials, if you synthesize, they may heat in some other mechanism. The heat mechanism, see, they have a high extinction coefficient. So large amount of absorbed energy is there. So that absorbed energy, it relaxes. The electron scattering happens, and electron phonon coupling arises, and all these lead to the energy being jumping between states and then relaxing, and you get the excess energy released in the form of heat. And NIR2 or NIR1 radiation have better penetration ability compared to UV radiation. NIR2 penetrates even better. Longer the wavelength, better is the penetration. So that is one example where you use. Here is one example you use silver gold alloy. These are observed as being dendrimers. They are formed in dendrimeric forms. The advantage of forming dendrimers is one thing that I explained in the last lecture. If they are non-spherical, they have a longer circulation time. So such non-spherical structures with larger aspect ratio are more interesting. And another interesting property is that they have a broad absorption. What is the advantage of having large absorption? A long range of absorption starting from 500 even up to 1000. See the broad absorption band. What is the advantage of that? You can excite at 808 or 1064 or even 690. You can use 3 kinds of lasers for one material. You do not design something for exciting at only one wavelength. You can excite at maybe 3 different wavelengths or 4 different wavelengths with one absorption spectrum, because the material has a broad absorption. The absorption also depends on shape, and now one material is commonly used, that is copper sulfide. Copper sulfide is also understood to have such a large absorption band in the NIR2 region. See, that is actually exactly centered at the 1100 or 1060 depending on the shape, and that is even more intense than the shorter wavelength band. So you can excite at the longer wavelength band and get and derive more of the photothermal efficiency. So you can simply synthesize the copper sulfide mixing a copper precursor and a sulfur precursor. This is what is being carried out in our lab also. Copper sulfide nanoparticles, the problem is the size is too small. As I said, we want them to be synthesized in the range that is best suitable for more circulation time, and we look for specific shape. We do not, we are not big fan of spherical particles. We look for non-spherical structure. So that is what one of our students is doing. 2 of my students are doing. Okay. Look at that. This is the photothermal conversion efficiency measured as a function of time. The temperature changes. The material absorbs radiation and gets heated. The heat increases up to certain time, and it becomes a constant, and then it falls down. When the laser is on, the material absorbs, material shows a heat change. So that heating efficiency may vary for different materials. It could be up to even 73 degree. Sometimes one report says that it is 80 degree, up to 80 degree they have heated, but we don't need 80 degree heating, because 43 degree is enough. 43 to 50 degrees is enough. If you are heating the material too much also, that may cause further damage. So you can optimize the heating efficiency, that is one thing, and the photothermal conversion efficiency, that is the relationship between how much radiation is absorbed and how much heating you can achieve using the materials. The photothermal conversion efficiency is what is more important, and the gold is having more photothermal conversion efficiency. The other parameters should be tuned at the size and shape, as I said. So newer and newer materials are studied. Near infrared absorbing materials based on lanthanide materials. Lanthanide based materials are also studied in detail. Yeah, we go to some nanoparticles that can be used for surgery. Why should you use an inorganic nanoparticle in surgery? See, one kind of surgery of tumor is employing fluorophores, organic fluorophores. They are functionalized with folic acid for example, they are concentrated in folate receptor overexpressed cells. That means cancer cells that overexpress folate. So they are specifically internalized in cancer cells. Now, when they are absorbed by the cells, you pass radiation and you illuminate actually the tumor. Why should you do that? You directly see the tumor, you can scissor it out, you should not say, because the tumor margin is difficult to identify. You find a clear margin when you are illuminating, especially when the tumor is deeply buried. In such cases, organic fluorophores get into such a tumor site if they are properly functionalized with ligands that are suitable for getting into cancer. So you scissor out when they are eliminated. This is a big area of research. One example is fluorescein, but problem associated with fluorescent molecules is that they have low quantum yield. They may undergo photo bleaching. They interact with unwanted tissues and the fluorescent signal is lost. In that case, you can use nano darts, quantum darts. They can be fluorescent, and when they are internalized, they are eliminated. When you pass radiation, they may be red fluorescent or green fluorescent. You can scissor out the tumor. The green is something which you normally observe. It is difficult to differentiate between the actual nanomaterial and the natural fluorescence of tissues. Only when the intensity of the nanomaterial is so large, they will be clearly different in margin. You can see the margin clearly. So red fluorescent materials are best suitable, and there you can use the quantum darts. So this is one example where these materials are smart responding to light. They are excited with the radiation, they have a specific absorption, they emit at a particular wavelength, making the materials, making the tissues fluoresce. So this is one comparison of the commercially available drugs, Alexa 488, all these refer to the wavelength 488, 608, 488. This is the absorption wavelength where you can excite and get the fluorescence. And you see here, the intensity of fluorescence loss is more in the case of the commercially available drugs, Alexa 488. But you observe the intensity of the quantum dot that can be excited at 608, that does not show a fall in the intensity. So that is the advantage of using quantum dots for such directed surgery, fluorescence directed surgery. Okay. So I'll go to the last part of our discussion. These materials act smart, they find application in biomedical field, and what comes next is molecular meshing. We discussed materials. Here I talk specifically like molecule. Why should we think of molecules as machines? Molecules functioning as machines. Molecules can work as machines. The world is constructed based on molecules. The entire world works on the principle of the employability of molecules. For instance, photosynthesis, some porphyrin like molecule chlorophyll that absorbs light, that acts like a light harvester. This you have studied, I think you have listened to that in some other lecture also, like a photo, I don't know, something related to light. I found some other lecture also. I didn't know the content of the lecture, but still I understand light harvesting. So that same principle is employed here. The nature is made of molecules, so we make use of them. Look at the structure. This is a Venus flytrap. This is a plant that is carnivorous. When some insect falls into that, it senses what is inside and it closes. That pressure on the inner epidermis builds a kind of fluid inside the plant and it closes. It has some sensory projections on the surface that also works in unison with the fluid that is inside the fly trap wings, they just close and they digest the insect. This is a Venus flytrap known to any environmentalist. The question is, how do you apply here? In what context you discuss this here? This is one machine that acts like having two stated equilibrium. One is the open state, one is the closed state. You can call that as on state and off state. Off state may be the open state and on state is the closed state. So that is a two-stated equilibrium. You can call that as a switch. You are learning from nature. One statement by one scientist says, just now I read, that states that everything is already made in the world by nature. You have to learn from that. We are mimicking nature. We try to mimic nature with our molecular factory carried out in the laboratory. We do a function of a molecular factory on our work table, and that's how we synthesize such structures. Can we design such smart structures? That is a question. Even though we are in the elementary stage, we have done a lot of magic with molecules and materials, mimicking nature. This is another stuff that is that the nature has designed. This is something like a wonder. Anyone who understands the function of the human sperm may tend to say this is the work of God. I do not believe much in the hand of God. I believe in science. It's not belief, it is understanding of science. You look at that. There are three parts: tail, the mitochondrion center, and the head piece and the tail piece. These three are connected. Middle piece carries the mitochondrion that is suitable for the fertilization, and you have in that sperm that the tail part. The head part and tail part, they are dictated with specific functions. I compare this structure with the Venus flytrap. The Venus flytrap is a two-stated structure. It is an on-off switch. Here, this is a machine that functions like a linear moving machine. You can compare that with a boat. You can compare that with fish. So it is a linear motion. So this has a kind of motion by which the tail is used to move. These sperm cells do wonder. They go hit the egg surface. You know the principle behind the fertilization. You know the function I am describing. It functions like a machine. So in that Venus flytrap, it can be called as one unified macroscopic structure, but this has three parts, something like a machine. This is an AT-pace motor. What happens is these alpha, beta, all these are protein globular structures. It rotates. Can you compare that with some machine on the macroscopic world? Yes. Wheel is the greatest invention in the world, and this AT-pace motor functions something like a wheel. It rotates, and the B structure, something acts like a lever that helps in the rotation. It stops the rotation, it allows the rotation depending on what kind of ion moves in. Potassium ion can move in, and it allows the opening and the swelling and contracting of these protein structures that can allow the rotation. It acts something like a turret. This is a wonderful motor, a molecular motor present in nature. Okay, so it could come in different parts that can be connected together. What comes to our mind when we say connecting parts together? It is supramolecular chemistry. Small fragments joined together to form larger structures. That's how we have to look at this molecular world. This is one example. This is one illustration of how a machine works. It has a coil, it has a plug, it has a fan. This is a heater. And how do you translate that into the molecular world? There is a receptor, a molecule that binds into that cavity. You have a connection. This is called a plug-in. that can be utilized in deriving a molecular machine. One of the dreams of nanotechnology is to design structures that pick something and drop somewhere else, something like a robo. We call that as a nano robo. Even though the nano robo definition is there, highly efficient nano robots are not in the nano size scale. Micro robots have been designed. Structures like the machines that work like bees, honey bees, they have been designed, but they are having structure sizes much more than a normal honey bee. To get into nano size scale, you cannot rely on smaller parts of materials. Maybe a plate or a string or a wire, you cannot have and connect them and have them in the nano size scale. To have them in the nano size scale, the best suited structures are molecules. That's why we look for molecular machines. Molecular machines operate like switching. This is you know about neonatal jaundice. When children are born, they may have some jaundice. They are put under light. What happens before phototherapy? They are having a kind of yellow color. They are cured after phototherapy. What is the reason? Bilirubin is there. This jaundice is connected to bilirubin. Bilirubin content should be less than 1, I think, in the blood. And if the content is more, the yellow color formation will be there, and that will reflect on the content of bilirubin in the urine and then in the blood. See, this is the structure of bilirubin being in straight form, molecule being a linear structure, and that can bend when light is passed. What is happening here? This is photochemical cis-trans isomerization. The double bond can bend. That particular wavelength can allow the bending of the molecule. What will happen now? When the conformation changes, it will not bind to the blood easily. So that will be eliminated. So one particular conformation only is suitable for residence in the blood for a longer period of time. So the conformation is changed when you are passing light. That's how we eliminate. Can you compare that with the two-stated equilibrium of Venus flytrap that also works on the principle of on-off switching? This can be called as on-off. When you pass light, it goes to the on state. When you are releasing the light, it goes to the off state. This is another example where the vision operates. What happens in the retina? There is a cis retinal. 11 cis retinal means that the double bond in the 11 position, that is in the cis configuration. When light falls on that double bond rotates, the double bond twists, it goes to the trans conformation, all trans conformation. The 11-12 bond twists. So it becomes a linear structure. The linear structure can bind to the protein in the rear part of the eye. So when it binds to the protein, a signal is induced. That signal goes to the brain. So when a light photon falls on the molecule retinal, there is observation of an object. That object goes to the brain. That signal is carried through the protein. So that's how it operates. This is the vision. This is actually the phenomenon of vision. That's how a natural molecular machine operates. I am discussing natural molecular machines. I discussed the case of macroscopic object, that is Venus flytrap. I discussed a case of microscopic motor, something which is a human sperm. And now I am coming to pure molecules. These are smart. These respond to light. Here is another basic molecular switch. You pass a photon of a particular wavelength. It goes to a conformation. This was first reported in 2001. The conformation based molecular switching in the context of just the change of conformation and the change of absorption wavelength. How is the output measured? It changes the structure and the absorption changes. So you call that input as the light photon and output as the absorption spectrum. Or you can revert that molecule to the original transposition by heating, by passing another radiation, a wavelength which is different from the original wavelength, or you can heat it. KBT refers to the heating. This is a nice representation of heating. Instead of putting a delta symbol, it is KBT. That is the best thermodynamic description of heat. So it goes back to the original state, it goes to the off state. From that, the concept of newer molecular machines where molecular switches were attempted in the laboratory to realize them in the context of molecules. Why molecules? Molecules are stable. One idea of nanotechnology is manipulating atoms, arranging atom by atom. This was debated long back when Richard Feynman expressed his vision, but chemists think the other way. It's easy for them to think in terms of arranging molecule by molecule because the scaling laws of molecules are well understood, the bondings are understood, the interactions between molecules are understood, weak bonds, supramolecular chemistry, everything is understood fully. So molecule by molecule arrangement is easy for them. That's how they understand. Molecules are stable species, atoms are difficult to handle. So nature starts from molecule and not from atom. So nature builds the world by molecular arrangements. You are dealing with molecules and not you are dealing with atoms. So the molecules can self-assemble also. The self-assembly can be exploited in designing structures. So this is one other example where cyclization is the switching. One is the open structure, the other one is the closed structure. When you pass UV light, the cyclization happens. When you pass visible light, the opening of the cycle happens. And both have wavelength of absorption in different range. So that is what is shown in the absorption spectrum here. So at about 550, there is absorption in one state, and in other state, the 550 absorption is not at all present. So you can call that presence of absorption. Color is referring to one state and colorless refers to the other state. So you know the functioning of molecules. They operate like switches, and how to assemble them on a substrate. You can do that kind of assembly on a surface. You have a gold nanoplate. You have a functionalization of this molecule with SH, thiol group. The thiol group has a great affinity for gold substrate. It forms it forms a semi-covalent bond. You call that a semi-covalent bond because the energy is half the size of the covalent bond. You call that a semi-covalent bond. It forms a semi-covalent bond with a gold substrate, and you have the molecule arranged on the surface, something like a brush. So now you have all these molecules on one substrate. You can make contact with this molecule from one end of them through an atomic force microscope tip that was realized in 2008. So you pass one electron, the molecule twists. You turn off the AFM tip, it changes its conformation. So you can manipulate the surface. I talked about switching. Here is another kind of rotation. Here is rotation of the molecule instead of just the flipping of the molecule. See, this is a molecule that rotates something half in one axis about the double bond. So this rotation motion is different from what you see in the case of diazo group earlier. So based on that inputs, molecular logic gates were developed. Light is one input. Why not having molecular inputs or ionic inputs? Two inputs, proton and sodium ion. These two inputs make this kind of molecules responding to the inputs, and the fluorescence is the output. And based on that, this is the first report on molecular logic gates. This is an AND gate, two inputs and you get one output. And that was published in Nature in 1993 by a professor now in UK and originally from Sri Lanka. So probably one Sri Lankan I like. Just to do something, we also did some work in the laboratory. We published that in Chemistry Open. Here the principle is that they form complex, cyclodextrin complex, host-guest complex. When host-guest complex is formed, the signal is enhanced. When the dissociation happens, the signal is low, and that this molecule responds to pH also. So pH is one input, cyclodextrin is another input. So based on that, we designed NAR gate and inhibit gate. Okay. So how is it applied now? All this work, of course, you mimic nature and you design structures, manipulating the molecules, playing with the molecules. How to apply? This is one example where the direct application is known. You look at the structure, there is a bicycle, which is a bicyclononane, diazobicyclononane. You see, there are the ring flips. It can flip like the wing of a bird. You can open like a wing of a bird and close. When does it close? When the two nitrogens are connected to copper ion, when they form complex with copper. So it could be calcium also, right? They can flip into two conformations. What is the advantage of that? You induce some stimulus and make the molecule respond to that. You put that molecule inside the liposome and other drug molecule also. Both are that inside, and what happens when the conformation of this particular molecule changes, it binds to the periphery of, I mean the internal surface of the liposome. When it binds, it disrupts the liposome, it opens. So at one particular conformation, when the wings are open, or when the wings are closed, the conformation changes, and there is an energy associated with that. At that particular conformation, it binds to the internal surface of the liposome and disrupts the surface, and it opens up the liposome, allowing the drug molecule to get released. This is one clever idea of molecular machines being used in real life applications, published in 21, some 2 months ago. Okay, I thank you for your patient listening. This is lunchtime, that's why I hurried up to complete. I think I have not taken a lot of time. I should thank my group members, the former group members and the current members, my PhD students. Some of them are working on magnetic nanoparticle for drug delivery. Some are working on NIR responsive nanoparticles. They synthesize cyclodextrin functionalized polymers. This is how our work goes. And if you have any discussion with me, you can contact me through email or through mobile also. Now you can open the session for some quick questions. Thank you for your patient listening.
Thank you, sir.
Again,
Participants?
I finished in 1 hour 29 minutes.
Yes, sir. Absolutely. Thank you very much, sir.
Yeah. Thank you.
Participants, you can post your queries in the chat box.
Hello, sir. Hello.
Yes, sir. Yeah.
Good afternoon, sir. Very nicely you in the nanoparticles for the treatment. How can you treat it? How they place in the final treatment?
Sorry, sir. I don't
Hello.
hear you. I don't hear you clearly.
You excellently presented, sir. The nanoparticles that how they in the biological field, especially in the cancer treatment.
Yeah.
So my question is that we can use the same way the nanoparticles in the heart, because they presently they using the angioplasty, that blood clotting stent they use.
Yes.
Why not the nanoparticles? You can inject nanoparticles by using electrofield or magnetic field, for particular that they can blast that blood clot in within the vessel, so that we can prevent this inserting this stent, so that may over a period of time it may side effects.
Very good question, sir. I understand that. For that, the surface of the nanoparticle, the nanoparticle surface should be designed with suitable molecules. Your question connects my original discussion and today's discussion. If the surface responds to some stimuli from outside, it can change conformation, or it can work on the clot and it can disrupt it. So of course that can be designed. The main thing comes from the surface property. The surface should be properly designed. It's a nice question. Thank you.
Thanks, sir. Is
Yes,
there
sir.
any research going on, sir?
Yes, yes, of course, yes.
Okay.
Yeah, that is going on. Yes.
Thank you, sir.
Very informative session. Thank you very much, Subha Moy Singha. Thank you, Anandavel. Is any hurdle in the preparation of hydrogel? Polymer design is known, it's a conventional preparation only. Functionalization of polymer, you have to choose specific chemical synthesis procedures. The hydrogel should not disrupt unwantedly. That is the main thing. It should not immediately decay or like that. So you have to design the polymer with a proper molecular weight and better water holding capacity. All right. Thank you, Mahesh Kumar. Thank you, Dr. Ratnam. Revati, Mrs. Yeah. Thank you very much.
Sir,
Yes.
can you all please enable your video for photo section? Dear participants, kindly enable your video for photo section. Thank you. Sir, can you please stop the screen sharing?
Is it stopped? Not yet?
Sir, yes sir. Thank you, sir.
Yeah.
It stopped. Thank you, sir, for your valuable and acclaimed presentation. Actually, the way you explained examples for smart material with real life are amazing, and again you are proving a best teacher and keen observer of nature. Thank you very much for your nice presentation, sir.
That's a nice comment. I enjoyed it. Thank you.
Thank you, sir.
Bye. See you.
Bye, sir. Thank you.
Bye. Bye.